All right, everybody, welcome back to the Additive Snack podcast. I'm your host, Fabian Alefeld, and today we're going nuclear. And we're going nuclear fission, to be specific. We've covered nuclear fusion in the past, but the impact on additive manufacturing or of additive manufacturing on nuclear fission is immediate, and it's happening today. And therefore, joining us today is Adam Travis, the Global Additive Manufacturing Program Leader at Westinghouse. Westinghouse, if you don't know them, they're a pioneer in the nuclear industry, but also now in additive manufacturing. And therefore, together we'll explore how additive manufacturing is not only revolutionizing the way we think about nuclear energy, but also how additive manufacturing is enhancing reliability and efficiency. So without any further ado, Adam, welcome to Additive Snack.
Hi, Fabian. Thanks for having me.
So, Adam, we've talked now in the past, and this is actually take two. We've had some technical difficulties on take one, but we've talked in the past, and one thing that still stuck with me and still amazes me today is that nuclear is an incredible energy source, not only from an engineering perspective, but also from a performance perspective. You've mentioned me that nuclear reactors have an uptime of 93%, which already today makes them the most stable power source we have. And the reason why I'm saying this is that typically we're trying to find additive manufacturing use cases in sectors where there are certain challenges with a system that we can optimize, where we can increase performance significantly, where we can increase supply chain challenges. But with a system that is so highly optimized today, what value are we finding through additive manufacturing?
So right off the bat, you said the two magic things, the two things that led me to this role and to getting into the nuclear industry, the 93% figure, and then what makes a good nuclear AM part, right? So I want to speak a bit more to each of those. So the 93% figure, it's actually a variable that we call capacity factor, very similar to uptime, but a little more nuanced because it also accounts for reduced power operations. So not just on or off, but if you're operating at X% of total power for a time, right? So it's essentially the total power output of a power plant, nuclear or otherwise, over a given length of time divided by the theoretical maximum power output over that span of time. And like you said, for nuclear in the US, I think the NRC figure is a 93% average. So what goes into that number to make it 93 for nuclear? Nuclear is extremely reliable, very consistent power generation source. We think and talk in fuel cycles in the nuclear industry. So fuel cycle is the length of time that a reactor is buttoned up and operating essentially, I won't say lights out, right? Because there's the control room and there's a whole host of folks that are keeping it well tuned and everything. The reactor vessel's sealed, the containment room sealed, and it's just steady state generating power. Typical fuel cycle, they vary, but typically it's about 18 months. So a year and a half is the typical fuel cycle that we see. So for say 17 months, continuous, uninterrupted operation, ideally. And then there's what we call a planned outage or a refuel. Mm-hmm. That typically takes about 1 month. So 17 months operation, 1 month planned outage, and then repeat that cycle. And in this month, I actually had the opportunity to go do an in situ inspection on an AM part last year during an outage at a plant. And
cool.
Hundreds, if not thousands, of Westinghouse employees and other suppliers and contractors will descend upon these power plants and perform an amazing volume of work in an amazing short period of time in a very small physical space, right? All without getting in each other's way. So this includes refueling, so taking all the fuel assemblies out, putting them in the spent fuel pool. A third of the fuel assemblies stay there. 2/3 come back and get rearranged into new positions. 1/3 new fuel gets loaded in. This includes a huge number of inspections, right? Mostly robotic, mostly remote, sending robots into places humans can't reach or shouldn't go because of lingering radiation, right? inspecting components, sometimes repairing those components, again, often remotely, sometimes replacing things as needed. So this huge amount of work takes place, and this is typically about a month that this takes to happen. So that gets you to 94% right there. So there's just that 1% really, that nagging 1% that we really want to target. And I'll come back to that later, or a little bit later. But to really put that 93% figure into perspective a little bit better, right? If we compare that to other energy sources, so coal and natural gas, they're at 40, 57% respectively. So even just comparing to the workhorses today, right, nuclear is exceptional. If we go a step further and compare nuclear to other low carbon energy sources, so wind and solar, those numbers go down to 35 and 25%. So even more significant gap. And that makes sense, right? How often is the wind blowing? How often is the sun out? Is it nighttime? Is it cloudy? Those things, right? Those have an impact. And this is not to rain. I shouldn't say rain. No pun intended. Not to rain on solar and wind. They absolutely have a place in the low carbon energy transition and low carbon future.
Yeah.
But with those types of capacity factors, right, and uncertainty in day-to-day, hour-to-hour power output, right, you can't build an energy grid, a reliable energy grid, purely on those things, right? You need something that really forms the backbone of those low carbon grids. And so nuclear really stands alone as the singular solution to that low carbon backbone for these future grids. So then we get into the question of what makes a good nuclear AM part. How, like you said, how do we add value into what's already highly efficient, extremely optimized environment? You can Google AM use cases and find lists that go anywhere from half dozen to a dozen to more. I would argue it all boils down to two use cases, right? AM is a design tool, and AM is in manufacturing, it includes supply chain, right? There's absolutely use cases, successful use cases for AM is purely as a manufacturing tool. But when you start with AM as a manufacturing tool, you almost always exclude the value potential of AM as a design is inherently upstream to manufacturing in most cases. Whereas if we start with AM as a design tool, you can typically reap some of the manufacturing benefits as you move through the process, right? So we always want to start in that design space. How can we use AM to add value to the things we do, the things we make, the services we provide? Typically, this is when you get into talks of design for AM and DFAM. You can call me a semantic prick if you want, but I'm not a huge fan of the DFAM term. It's an inherently limiting term, right? Design for, it sounds like we're trying to fit our part peg into an AM-shaped hole. And there are considerations, right? Lattice supports and overhangs and those sorts of things that absolutely are critical to being successful. But I think typically what we mean by that is that there's a design freedom inherent in it that we can take advantage of. And so I've always preferred the term design for purpose, right? Whether it's machining, casting, whatever conventional process, we should always be designing parts for purpose, and whichever manufacturing method most fully allows you to realize that purpose in the design, that's a really good starting place to build a successful business case. There's exceptions. If your cost is 10x and your gain is marginal, that may not solve it. If you can more fully design for purpose with AM, that's a great place to start building a successful business case for AM. I was just watching a podcast last month with Joe Laurienti from Ursa Major, and he said something that really resonated with me, especially thinking about this conversation that we were about to have, and that we want to be applying AM to industries where cost per part is really high. So typically aero, medical, jewelry, right? And he's not wrong. I mean, that's absolutely correct. And I think that's a lot of the success stories we hear are built around that mode of attack and that use case, right? Lightweighting and reducing that material cost. But that's not nuclear. That's not a problem that we face, right? Nuclear reactors are static. There's a NASA project in talks of putting a nuclear reactor on the moon to power lunar settlement, lunar outpost. But by and large, typically that one thing accepted, right? Nuclear reactors are static things that sit. The reactor core itself is static. You're flowing coolant through it, not the other way around. There's not rotating components inside of there. So we're not too worried about weight. There are some exotic materials in a nuclear reactor. Obviously, uranium is another one. But by and large, a lot of stainless steel, a lot of Inconels, not typically materials that we think of as an exorbitantly high cost per weight, right, in terms of material costs themselves. So again, the question, what makes a good nuclear part? And it all comes back to that capacity factor, that 93% I said there was that 1%, right? There's that 1% below added on to the 6% you get from these planned outages. And so that's really what we want to attack and try to remove that one
Mm-hmm.
and get as close to that theoretical perfect number as we can. There's a number of things that can cause dips and pauses and low power operations for short periods of time throughout a fuel cycle. But one of the most not common, because they are in fact very uncommon, but one of the higher profile and probably least desirable incidences, or that can occur, are what we call leakers. And so this is when a fuel rod gets worn through and exposes the uranium pellets inside to the coolant loop, and so then there's an escape of uranium into the coolant loop. Highly
Mm-hmm.
undesirable, causes issues for the utilities, the power companies. In most severe case, can cause an unplanned outage, right, where they have to go in, shut the reactor down, open it up, remove that fuel assembly, and replace it with a new one, which is not something that they want to be doing. And so that adds up. The one small instance in one reactor somewhere, right, has a noticeable impact on that kind of industry average value. So immediately, then we start thinking, I should say, actually, what causes leakers? And one of the primary causes is debris in the coolant loop. And I want to couch that for the non-nuclear audience when I say debris in the coolant loop. Nuclear reactors, nuclear power plants, and nuclear coolant loops are extremely clean environments, very well maintained, very high standards. But it takes a surprisingly small amount of very fine debris that can cause damage in a nuclear reactor to a fuel assembly. And I'll put a figure, some size to that here in a few minutes to tell you what that limit is that we're talking about. So we want to mitigate, minimize, reduce the potential for these leaker events to occur. And so that means debris filtration, right? We want to filter out debris. Typically, almost always, that is in direct opposition to another critical parameter of a reactor, pressure drop. Right, we want to always minimize the pressure drop of the coolant going through the core to maximize the end of the cycle. Right, the energy we're spending pumping the coolant through, the less efficient our overall cycle is. Maximize debris capture, but minimize pressure drop, or ideally don't impact it at all. Find a way to filter better, don't pressure drop in any way. And that's a really good starting place to say, how can I use to improve nuclear power? So I've actually got two parts today we can talk about that kind of answer that question or speak to that question. The first, I don't have with me, but we call it the Stronghold AEM filter. There was a Stronghold conventional filter, and then the AEM version of it came after. If folks Google Westinghouse Stronghold, they can easily find some pictures of what that part, or at least the first version of that part, looked like. We're on version 3 now of.
Oh wow.
And when I say version, not improving, not changing the original, but for different types of reactors, right? So we made version 1 for a specific fuel bundle, fuel assembly that we sell, and then version 2 and 3 for other fuel assemblies. But I guess to give folks an idea of what it looks like, it's not dissimilar to the tungsten X-ray backscatter grids that we've probably all seen pictures of that have been printed. So on the outside, fairly innocuous looking box with a really fine square grid pattern in it with flow channels through it. And then on the inside is the secret sauce, what we call the tortuous path, where we've used AEM to create some really elegant internal debris filtering features that you wouldn't be able to do any other way than with AEM. And to get an idea of really the value that AEM has brought to the debris filtering fight, so to speak, in boiling water reactors, I was talking about how small of debris we have to contend ourselves with, right? The lower threshold, there's a lot of data and operational experience to say the lower threshold of data that can damage a fuel assembly or a fuel rod over the life cycle of a fuel assembly is a 5 millimeter piece of wire. And that's not a 5 millimeter diameter piece of wire, right? It's like a single strand of wire, 5 millimeters in length, rocketing through the coolant loop over and over and impacting off of fuel rods can over time wear through, right? Hitting in the wrong place, the wrong number of times. So that's the lower threshold that we in the industry have always been aiming for to capture that size of debris. With the conventional Stronghold filter, we were able to achieve 100% filtration down to 7 millimeter wire length. Pretty good, but obviously there's still enough debris in that space below that can cause very infrequent leakers. With AEM, we have achieved 100% debris filtration down to that 5 millimeter wire length size. So essentially, AEM has come in and been able to be the ultimate answer to this question of, or this desire to remove debris or remove debris related failure mechanisms from boiling water reactors.
Interesting. So almost a 50% reduction in filter size by maintaining the same pressure drop requirements.
Correct. Yeah. With AEM, we're able to keep pressure drop by and large unchanged, and then reduce that minimum debris size that can get through the filter by a substantial amount.
Yeah, that's awesome.
Yeah. And then the second part I do actually have with me, so I can show this guy. We call this the additively manufactured bottom nozzle, so AMBN. It performs a similar function to the stronghold filter, but in pressurized water reactors. So we were talking boiling water reactors before, now we're in pressurized water reactor space, PWR space. So this guy I have here with me, that's an AMBN. This is the outlet side of it. The AMBN sits in a reactor like this. Coolant comes up from the bottom, so this is the outlet side. And this is actually the very bottom component in PWR nuclear fuel assembly. Each one of these vertices here, where these larger ligaments connect, is where a fuel rod sits. So they actually sit directly on this plate. And so fuel assembly is being hoisted or carried around. All of the weight of the fuel rods and the fuel assembly are sitting and resting on this plate. It also is critical, right, that the strength be there for accident conditions as well, or seismic events, right, if it needs to bear additional weight. There's actually a test they do, they call a drop test, which is the most extreme test they do with these on the structural side of things, where if it assumes while it's being hoisted or relocated, if it were to fall right off a crane by accident, is this guy going to stand up and hold all the weight of that fuel assembly? And so they'll drop these things and see how they perform. And AMBN is rock solid. This is a 17 by
Very cool.
AMBN, we call it. So there's 17 fuel rods by 17 fuel rods that make up a single fuel assembly. And then there'd be a couple hundred of these fuel assemblies in a PWR reactor. I'll hold it up here. Hopefully my camera's cooperating, but hopefully in between these large ligaments, you can see these finer mesh features. And hopefully if I rotate it, you can get a sense that it's not 2D, right? That's not a flat mesh. There's an axial component to that mesh. And so again, with we've been able to create this really advanced mesh shape and structure that's highly efficient at capturing debris, but again, doesn't really meaningfully impact pressure drop. So to put some numbers to this guy, on the PWR side of things, I think it's a 13x reduction actually in debris size that we've been able to achieve from the latest and greatest conventional filter that preceded this. And that took us from a 65% debris filtering efficiency all the way up to 96%. So really exceptional gains being unlocked with as a design tool in both of these applications.
Wow. And this is a highly critical part, huh? This is not just...
in nuclear, the term we use is safety related, right? Safety related components, safety related parts. That's nuclear's version. That is to nuclear as flight critical is to aerospace, right? So both of these parts are the highest level of quality, component quality classification that we have in nuclear. So very encouraging and very exciting to see AEM being deployed up to this level of component qualification already in nuclear.
Yeah, no, it's very encouraging, I think, for the whole industry to see you guys adopt additive in such critical applications and to see the performance improvements that are so significant, right? The first part, 50% in filter size, this one 13x. Those are very significant performance improvements through the performance-driven design aspect that you mentioned early on. What about the supply chain or manufacturing aspect? Have you guys identified any applications in that space as well? Or would you even say these two applications we just talked about kind of combine the design and manufacturing aspect?
Yeah, certainly there are manufacturing aspects that we take advantage of, but really it's predominantly the design, right? It's improving functional performance, what the parts are meant to do through the design space. And I know I talked down on manufacturing as a use case for AM earlier, but we do actually, we have a part that also falls into that space, right? I would say in my experience in nuclear and beyond, it's much rarer that we find a part, at least a part that's in a high quality classification family where manufacturing alone really builds the business case, but it certainly does happen. So I have this guy here with me today. It's actually a pair of parts, two parts that make a pair. These are called flow plates for a third type of reactor called VVER type reactors, which is a Russian acronym. I believe essentially means water reactor. You have a bottom flow plate here and a top flow plate over here. And so these would sit on opposite ends of the fuel assembly, much farther apart than my arms can reach, providing specific benefits to the fuel assemblies to shape the flow, manage the flow, and then also constrain the fuel rods in there. So with this piece, this looks by and large almost identical to what the conventional version of these parts would look like, right? There's not significant design for AM going on with these parts. Certainly tolerancing for AM was critical to successful deployment, right? If we had kept the drawings that had all the machine surface call outs and requirements on it, the business case for AM would have fallen apart very quickly. But working with the teams and the product owners and their willingness to really understand AM and have honest conversations about, okay, where do we have vestigial tolerances versus critical tolerances was absolutely critical to the success of this application. There's actually a list of supply chain or manufacturing benefits that we were able to realize with this pair of parts. They don't fit together in the reactor, but they do fit together, which I just find really satisfying that they
Yeah.
these pins perfectly slot into the holes there. I just find that really satisfying. So the manufacturing benefits with this guy, I guess some context and some history on where this whole effort came about. As I said, VVER type reactors are Russian designed, originally Soviet designed reactors. They're very prominent in Eastern European countries. I believe there's something like 90 of them in six or so Eastern European countries, including Ukraine, right? And so there had been interest in developing Western sources of fuel for VVR type reactors for years. When Russia invaded Ukraine in 2022, that suddenly created a very urgent need, specifically for Ukraine, right? If they were going to keep their reactors running, they had to have an alternative fuel source. But more broadly, just for Eastern European countries that have this type of reactor, to have that diversity of fuel supply, they weren't solely dependent on Russian fuel to fuel their reactors. So very rapidly, over a total span of 18 months, right, this part was designed, developed, tested. When we say 18 months, that's not just time spent playing on the printer. That's printing, sending things to our testing facilities where they have functional rigs that do debris testing, pressure drop testing, loss of coolant simulations, a whole host of functional tests, right? They actually build mock field assemblies and have these specialized test rigs. And those things don't happen overnight, right? So the AM
Mm-hmm.
portion of this was probably closer to 12 months or 9 months even really of time spent on the printer developing this, adapting what were conventional requirements and adapting them to AM and then building the qualification around it. Additionally, on the cost, this actually AM actually beat raw machining on per part component cost. So I'd say solely manufacturing use cases are rare and high quality applications. Cost competitive business cases or cost beating business cases are even more rare. But here's proof that it can happen. There's part consolidation going on here. So typically the bottom flow plate would be a wrought plate and then a stamped skirt that got welded together. That's now one piece, obviously. And then this top flow plate would be a wrought spiderweb flow plate here. And then these pins would be welded in. And that's all one monolithic piece. So we went from 9 parts down to 2 parts. In doing that, we also increased the strength of both of these components substantially over what they would have been if they were relying on those welds. So that provides an even higher safety margin, higher strength in accident conditions. As I said, this was a critical need for Ukraine to keep their reactor fleet running. So the first commercial delivery of these parts was made in August of last year, August 2023, to the first Ukrainian reactor. We actually started production serial production on these towards the beginning of last year. And just last month, we celebrated the 1,000th part produced in this family here. And again, these are safety related parts, right? So we're very, very excited and very proud of that milestone of having produced 1,000 safety related end use nuclear components with AEM at this point.
Yeah, that's incredible. If you think about it, in 18 months from demand through redesign all the way into then, and now just a few months, really half a year later, you're at 1,000 parts, is a really impressive timeline for a safety critical industry as nuclear. And looking at the parts that you just showed, they are also quite complex. So I could definitely see the cost comparison being positive towards additive in comparison to machining. I'm really curious because you guys have such advanced application programs and that doesn't happen overnight. What did the journey of Westinghouse into additive look like?
Yeah.
How did this start, and how did you guys evolve into this advanced state where you are at?
Yeah, sure. AEM at Westinghouse goes back a little over a decade. Probably about 2013 is when activities first started. And really, that inciting incident was the right technical person at a conference, not an AEM conference, but probably at the nuclear conference, saw some presentation on AEM and saw the potential, saw that, hey, this is something really new that has that design potential in it. We should be looking at this. And it really was a bottom up effort for a few years of really this core of technical folks saying, hey, we really see value in this. And it was probably still a little too new, especially in the nuclear space, for kind of the company as a whole to really latch onto it at that point. Those folks fought the good fight, so to speak, and really kept putting it out there and showing and demonstrating through some really smartly ordered milestones of the potential for AEM and the readiness of AEM to be deployed in these applications. So that the first big milestone there was in 2015. Westinghouse conducted one of the first, if not the first ever, AEM material irradiation studies at the MIT reactor. So we printed some AEM specimens, put them in the MIT reactor, cooked them for a while, pulled those out, did what we call a PIE, post-irradiation examination, same as any other characterization effort, right? With the added complexity that all the parts are now highly irradiated. So there's only a handful of labs in the world really that can handle these types of hot materials, so to speak. Westinghouse at our Churchill facility outside of Pittsburgh actually operates one of the only private labs that are rated to handle these kinds of materials. So they have all the characterization equipment you'd expect in any decent lab, but it's in these cells behind an extremely thick glass with these robotic arms coming down from the ceiling that operators and engineers can operate from these really cool articulated controls outside. It amazes me, they can run SEM equipment, they can run tinsel test machines, they can run machining centers to machine coupons and the grips and everything down. And really just cool to me that's like a skill set that some people have to be able to do this like highly specialized kind of work. And the fact they can just operate relatively normal pieces of equipment using these specialized robotic arms. We did that. We published that data, right? We viewed that not only as important for Westinghouse, but important for the nuclear industry as a whole, really on our acceptance curve of AEM, getting folks amenable to the idea and to say, hey, look, AEM really shows promise. And the high level takeaway from that data and that effort was that for the critical mechanical properties and parameters that we're concerned with, AEM holds up largely identically to conventional materials in a highly irradiated environment. There's plenty of industries that are all concerned with fatigue and strength and everything else. We had the added complexity of, okay, what does it hold up? How does it hold up under neutron bombardment? And so we were able to demonstrate that it holds up largely identically to conventional materials, which was really the first big call it win or enabler, right, for getting AEM into nuclear applications. So with that data in hand, the team set out to say, okay, let's get a part in an operating commercial nuclear reactor now. That's really the next step. We've proven the materials can hold up to it. Let's get a part in and show that the components can hold up and still perform their function. So in 2020, Westinghouse inserted the first ever safety related LUA, which is an industry term for lead usage assembly. It basically means first of a kind for any given component, right? the lead usage assembly, the first of its kind to be put into an actual commercial, operating commercial nuclear power plant. So the first AEM LUA. Don't have this guy with me either, but folks can Google Westinghouse thimble plugging device, and you can see pictures of it. So this thimble
Mm-hmm.
plugging device, or TPD, was the first ever part put into a nuclear reactor. Not a commercial part, purely as a demonstrator, right? It was safety related, so it did fall into our highest quality classification. I actually give the team a hard time because not only was it the first ever AEM part, it's actually a hybrid part. We took half of the part that has big coils and springs in it that wouldn't have made sense to print. We loaded that into a printer and then printed the AEM part off of that. So we're actually not only going to get data on AEM materials, but also that interface as well. And I give them a hard time. That was a really big swing to take on the first part. But we inspect it every 18 months. We go into a visual inspection. It's holding up perfectly well. Will be coming out this fall. It might be this fall. It's coming up in the next couple outages. That part will be coming out for good. And then we'll start the long process of letting it cool down a little bit and then doing the PIE on that and publishing that data as well. Jump ahead another 2 years. In 2022, we had our first ever commercial LUA. So that's the stronghold filter I was talking about, that first part I was talking about. 2022,
Mm-hmm.
that was inserted. Maybe not as big of a milestone for others as it is for me, but that's the first, I call it commercial LUA, right? It's the first part, AEM part ever put into an operating nuclear power plant that really added value to that plant. It wasn't a demonstrator. It wasn't a proof of concept. It actually was doing something that we couldn't do any other way. So that part's been cooking for 2 years now. It'll also come out for its final time here in the next year or so. And then I guess some other context I should give is how this whole LUA process works in the nuclear industry. Is typically you'll do an LUA, you'll print 4 to 8 of a given part, put them in one reactor, let them sit for 3 fuel cycles. So anywhere from 3 years to say 4.5 years, then they come out, do the PIE, results are good, then you go into serial production, or what we call region quantity deliveries of a part. So we're in that intermediate phase right now where we're gearing up for serial production on that component here in the near future. 2023, just last year, right, we talked about the VVER flow plates. That was our first ever serial production of a safety related AEM part. If you plot out those points, I think you see a really strong connective tissue of, okay, materials, component demonstrator, adding value, going into serial volumes, right? You really see that ramp up. And if you plot them by date, that it's accelerating, right? The curve is starting to increase and really take off. And I think it's a really exciting point in time to be in nuclear AEM as we start to rocket up that curve and really see where AEM can take us.
Yeah. I think if someone were to write a book on how to successfully implement additive manufacturing into a new industry, that should be the path, right? Start with a demonstrator that is critical to the organization, but can also show the potential and risks of an additive part, and then really go with an application next that leverages the full potential of additive, especially on the design side. And I think that also hopefully, and I'm guessing, give more confidence and exposure towards additive manufacture within Westinghouse, beyond just the AM team, but beyond into other teams, from engineering all the way into operations, I'm guessing.
Yeah, it's a snowball, right? The more success, the more folks are willing to accept it. And the more folks are willing to accept it, the more opportunities you have to be successful, right? And it just keeps building on itself.
Yeah, exactly. Okay, I want to talk a little bit about the future as well.
Sure.
And that is, you now celebrated the 1000th part. You've had now more than a decade of additive experience under the Westinghouse belt. Whoops. What's next for additive at Westinghouse? What can we expect?
Yeah, so I'm extremely proud of. I joined Westinghouse a few years ago, right? So some of this, a good portion of this body of work predates me, right? So I have an immense amount of respect and admiration for the work that was done prior to that date, and an immense amount of pride in the work that we've done since then, in the body of work that's been accomplished to date. But that said, we've just scratched the surface. These are applications that are existing applications that we've been able to convert to AEM. And we've been successful in being able to play not only in the manufacturing space, but in the design space for these existing applications, which sometimes can be really prohibitive, right? For an existing application, something that's out there and defined, it can be very difficult more bureaucratically than anything, to say, hey, let me change that thing that already works and does good enough, so to speak. We look forward, there's a lot of blank paper ahead of us and opportunities that haven't been written down yet or defined or put into a box. And so we have the opportunity to think about them as additive first applications. Some of these spaces for us is the AP300, which is a new class of reactor called small modular reactors, or SMRs. So lower power output than a traditional nuclear power plant. So like right now, our biggest plant, the AP1000, is like 1100, 1200 megawatts electricity. AP300 is 300 megawatts electricity power output, but also smaller footprint, smaller capital cost, which is something that has really been a request or demand from utility companies. They don't want the projects and capital costs they have to incur. They want to be able to grow or grow nuclear at a smaller chunk, so to speak, right? So AP300, we have the Vinci microreactor. So this is an even smaller class of reactor. So we had 1200 megawatt, 300 megawatt. Vinci's like 5 megawatt electricity, right? So orders of magnitude smaller, right? This is really aimed at remote locations, remote towns that might have to run on diesel generators, or remote mining locations or facilities like that. Also, a small, relatively economical package for universities, right, to get access to neutrons, to do neutron bombardment studies and that sort of stuff. So Vinci AP300 present host of new opportunities and blank pieces of paper to look at, with a building off of a Vinci. I mentioned, I think towards the beginning, this NASA project called Fission Surface Power, FSP, for a lunar reactor. That gets me really excited, right? You combine all the cool things that we're learning to do with AM and nuclear with the most tried and true use case for AM ever of take the weight out of stuff and launch it up into space, right? So really cool opportunities there to see how we can leverage AM to do things that have never been done before. Like I said a while ago too, right? A lot of stainless steels, a lot of Inconels. We're actively developing a number of either new materials to AM or outright novel materials that are more commonly found in nuclear applications that are going to open up some really cool opportunities. Everything we talked about today was laser powder bed fusion. We're looking at other modalities now, right? Getting into bigger parts. So you can imagine the modalities involved there. And the last really big one is the ASME boiler pressure vessel code, right? There's not a codified pathway for AM there yet. ASME BPVC is very big in a lot of nuclear components, especially on the plant side of things. And so that'll open up a whole new host of opportunities for us when that time comes. So if we go back to the plot of the story up till now, and then what does that future look like? It's not just the slope increasing, but it's broadening too, right? You have to add an extra axis to it. We're going from this point to this cone that's shooting out to new materials, new modalities, new types of use cases. So it's exciting times, to say the least.
Yeah, very exciting. Starting more than a decade ago, it seems like you guys are now at a point where this acceleration can really start happening. You have all the experience, resources in-house, and you've built a network also of suppliers, I'm sure, that can help and support that growth curve. Adam, it was really awesome to have you on the show today. I didn't only learn about the additive use cases at nuclear, I also learned a lot about the nuclear industry. So thank you very much for that. I think it's a underestimated technology that has such a big impact on our daily lives. So thank you for enlightening us in that space. And it's truly exciting to see where the journey is going to go towards microreactors and also towards the moon. So Adam, thanks again for being on Additive Snack. It was a pleasure having you on the show.
Thanks for having me. It was a lot of fun.
And thank you out there for listening to the Additive Snack podcast. It really means a lot to us that you've been sharing this journey with us, where we all get to listen to the amazing stories from some of the most influential people in the additive manufacturing industry. And over the past few years, we've also gotten some great comments and ideas from our regular listeners, like you, John Manley, and you, Kristen Kerner, and many more. You've really all helped us to continuously improve and build a better podcast episode over episode. And whether if it's your first time listening to our podcast, or if you are a regular listener like John and Kristen, please always feel free to send over some feedback, give us ideas for guests, or just any thoughts that you might have by either commenting in YouTube or sending us an email at additive.snack@eos-na.com. We're going to take a little break here, but don't worry, we'll be back very shortly with the next set of great leaders, interesting stories, and innovative ideas all around additive manufacturing here at the Additive Snack Podcast. I'll see you then.